In this video, we'll look at how to apply our knowledge about transformations of functions. So here we have an example of a function, f of x equals x plus 3 squared minus 5. The first thing we want to do is state the parent function, which means you're going to look at the function that you have and think about the overall thing that's happening to this function. So you see that something is being squared, and that's going to tell us that our parent function, which we'll call g of x, is equal to x squared. So now we'll talk about how we can obtain this new function f of x by transforming g of x using what we know about shifting vertically, horizontally, reflecting, or stretching or compressing. So again, we're just talking about how to transform g of x to obtain f of x. So we see two things are happening. We're adding 3 inside parentheses and then subtracting 5 on the outside of the parentheses. Adding the 3 on the inside is going to result in a horizontal shift. So we're shifting g of x to the left 3 units. Remember, if you're adding, you're shifting to the left if it's on the inside. And then since we're subtracting 5, that means we're going down 5 units. So now we can go ahead and take this information and sketch a graph. So I'm just going to fast forward this a little bit to get the grid down. Okay, so this is my parent function. This is just regular xy plane. I have my axes marked out to 5. This is my parent function g of x that's drawn. So just by looking at this parent function, I can shift it using what I already know and get our new function f of x. So I really am taking every single point on the graph of g of x and moving it left 3 units and down 5. I'm going to just focus on these 3 points here. So I've moved this first one left 3 units and down 5, and I'll do the same with these. So left 3 units to here, and then down 5 units. Once again with this point, left 3 and down 5. I can do that with the other points that I have marked or any other points on this graph, but just getting those 3 really gives me a good idea of where that parabola lies, and I could just go ahead and sketch it. Remember, the shape of the function will be the same as the parent function. So what I just have drawn here is f of x. Alright, so now we have our sketch. We can talk about domain and range. And we're talking about domain and range of f of x. So we're focusing on this picture here. For all parabolas, our domain will be all real numbers. That's from negative infinity to positive infinity. That doesn't change when I shift. But the range does change when I shift my graph, because it depends on where this vertex point is. So my range is going to be everything from negative 5 to positive infinity. Negative 5 is included because it is a point on the graph. Okay, so let's take a look at our next example. So here I'm going to give you a graph of a function. The graph I'm actually giving you is of sine of x. We haven't really talked about sine, so I'm just going to give you the picture. Sine is a trig function, so the inputs are angles, and these angles are labeled in degrees, and the outputs are ratios. So I'm going to label 1 and negative 1 on my axis. So I'm going to plot some points here to get a shape of the graph, and then we're going to use this graph to obtain some new functions. So again, this is what's given to you. This is not something that you need to know at this point. Now, sine curves are nice and curvy. They're waves. So we have this nice smooth curve connecting these points. Alright, so the first thing we want to do here is sketch a new function, f of x, which will be equal to 2 times g of x. So I'm multiplying g of x by 2. If I multiply by 2 on the outside of the function, that means that the effect is a vertical stretch. So again, this 2 here tells me I'm going to take my original graph and stretch it vertically, and that's by a factor of 2. Now, in order to do that, I have to multiply all of the y values of these ordered pairs by 2. So I'm going to do that by just creating a table. I'm going to list the ordered pairs of g of x, and then I'm going to go ahead and list the ordered pairs 2 times g of x, which means, again, just multiplying the y values by 2 because it's a vertical stretch. So let me just fast forward here and get the points for g of x down. Fast forward. Okay, oh, I got them all down. Alright, so these are my points for g of x. I just took these off of the graph here. And then now I'm taking each of these ordered pairs, taking the y values only, and multiplying them by 2. So the first ordered pair doesn't change, but the second one goes from 91 to now 92. Third ordered pair does not change, but the fourth one goes from 270 negative 1 to 270 negative 2. And the last ordered pair also does not change because the y-coordinate is 0. Once I plot these ordered pairs on the same graph here, as you see is done, my graph appears to have been stretched vertically. So if I imagine that this were on a piece of rubber and I could just pull it vertically, it pulls it upward and downward at the same time. So I have the same width of that graph, but the vertical height has changed. So the taller one is f of x, and the smaller one is our original parent function, g of x. So now we're going to do something similar. We're going to, again, refer back to g of x, but we want to create a new function, which we will call h of x. So we're going to sketch h of x equals, but now we're going to multiply by 3 on the inside, so g of 3 of x. So notice I'm multiplying x, not the entire function. If you multiply the inside of the parentheses, that results in a horizontal stretch or compression. In this case, it's a compression because the value that we're multiplying by is greater than 1. Now, in order to actually perform this transformation, that means we're going to multiply the x values of g of x by 1/3. Remember, with the horizontal compression, you're taking the reciprocal and multiplying the x value. So we can do the same thing, create our table of values, list the ordered pairs for g of x, and then the ordered pairs for g of 3x. So good, I'm listing the same ordered pairs from g of x that I had before. But now, in order to perform the transformation, I'm taking all of the x values, multiplying them by 1/3. That's essentially dividing them by 3. So the first ordered pair doesn't change, but the second one does. It turns into 31. Next I have 60, 0, 90, negative 1, and then 120, 0. So then all of these x values have been multiplied, or resulting from multiplying the previous by 1/3, or dividing by 3. So then I could go ahead and plot these ordered pairs. I'm going to do that on the same axes. So I have to create my scale in here, so I'm just dividing that segment from 0 to 90 by 3. I'm plotting that first point at 31. That third point is at 60, 0, and then I'm at 90, negative 1, And then I need to go here. Again, I'm going to split this section into thirds, and that's my last point, 120, 0. So right in here will be my curve. It has the same shape as the original, it's just been compressed horizontally. So if you imagine we took our original curve, g of x here, pushed it together horizontally, the height is not changing, but the width between each of these waves is now changing horizontally. Okay, so let's take a look at our next example. Before we do that, we have to just talk briefly about order of transformations. So what we'll do is see how to deal with having more than one transformation at a time. And this order can change, depending on your function. You don't have to always do your transformations in this order, but it's certainly a good way to start. Alright, so your order of transformations really have 3 steps. Your first step is to perform any reflections, and that's over the x-axis or the y-axis. After you perform any reflections, you are then going to perform any compressions or stretches that you have. And it doesn't matter if they're vertical or horizontal, you can do them in the second step. Finally, you can perform any shifts, vertical or horizontal shifts. And again, this is just a suggestion. Sometimes you can rearrange the order of transformations, but if you follow this, then you can't go wrong. Alright, so our third example we have f of x equals 3 over x minus 2 plus 1. And the first thing we want to do here is state the parent function. And it might not be so obvious what our parent function is, so I'm going to manipulate this equation a little bit by factoring out this 3 in the numerator. So f of x is equal to, taking out a 3, so it's 3 times 1 over x minus 2, and then plus 1 on the outside. So now I see that it has that 1 over x, that reciprocal function, which means my parent function is g of x equals 1 over x. So now I want to describe how to transform g of x to obtain f of x. And I have a couple of things happening here. So I see them multiplying by 3, I'm subtracting 2 but inside the parentheses, and then I'm adding 1 but outside of the parentheses. So that means that I'll have 3 transformations happening. Alright, so the first thing, if I refer here, I don't have any reflections, there's no negative, but this 3 is being multiplied on the outside, so that gives me a vertical stretch, and that's by a factor of 3. Inside here I have a minus 2, that's inside the function, so that's shifting to the right. 2 units, and then this plus 1 is a shift upward by 1 unit. Okay, so just running out of a little time here, so here's our last example. You can certainly pause this and read through it. But again, we're doing the same thing. We have f of x, and we want to state the parent function. We see the square root, so we know our parent is a square root function. Our transformations, again, we're going to play around with it a little bit, factor things out so that we can see really what's happening. And then we'll see that we have a reflection over the y-axis. We're shifting to the right 1 unit because of that minus 1 on the inside, and then up 2 units from the plus 2 on the outside. Again, take a look at this manipulation here to see exactly what's